Today, we need to talk about a completely new way to build artificial intelligence. And I'm not just talking about a bigger algorithm. We're talking about an AI that lives and thinks in a universe with its own unique set of physical laws. Let's get into it. This quote, it just gets right to the heart of the matter, doesn't it? The most advanced AI systems being developed today are changing the very space where thought happens. So I want you to forget the flat, grid-like world of normal computers. We're about to step into a world of curves, of causality, and of pure geometry. But, to really get why we need a whole new universe, we first have to understand the crisis that's brewing in our current one. Some researchers are even calling it AI's flatland crisis. It's a question you've probably asked yourself. How can a model that seems to know everything suddenly just make stuff up or totally lose the thread of a long conversation? Well, the answer isn't about more memory or faster processors. It's a problem of geometry. It's a housing crisis for information. This right here is a perfect analogy. Think about your own family tree for a second. You have 2 parents, right? And 4 grandparents, 8 great-grandparents. The number just explodes. It grows exponentially with every single generation. Now, imagine trying to lay out a photo of every one of them on your living room floor. At first, it's pretty easy. But very, very quickly, you've got a massive problem. The floor space, your room, it only gets bigger in a linear way. But that family tree is growing exponentially. You just run out of room. You're forced to start stacking photos on top of each other, mixing up your great-great-aunt from one side with a distant cousin from the other. The connections get lost, and the history gets all muddled. And that is exactly what's happening inside our current AIs. The technical term is oversquashing, or a geometric capacity bottleneck. We are trying to cram exponentially complex stuff, like language or logic, into a flat, limited mathematical space. The AI literally runs out of real estate and has to stack unrelated ideas together, and that's what causes the confusion, the distortion, and those infamous hallucinations. So if a flat universe is the problem, what on earth is the solution? Well, it's to give the AI a brand new universe to live in, one that has a very different shape, something much more organic. This is the big aha moment. What if the container could grow at the same incredible rate as the content inside it? What if the AI's universe had practically infinite room for every single branch of that family tree, no matter how far back you want it to go? Well, that kind of universe actually exists in mathematics. It's called hyperbolic space. So don't picture a boring, flat sheet of paper. I want you to picture a kale leaf, or maybe a piece of coral. You see all those wrinkles and folds? They evolved that way for one reason: to maximize surface area. That's a great way to think about hyperbolic space. It's a universe that's always creating excess area, constantly curving away from itself to make more and more room. And this slide just lays out the difference perfectly. On the one hand, our old AIs were living on a flat sheet of paper. The volume grows slowly, and information inevitably gets squashed. But on the other hand, this new architecture gives the AI a universe shaped like that kale leaf, where the volume grows exponentially. There's always enough room, which means all those complex hierarchies and relationships can be preserved perfectly. Okay, so we have this amazing new curved universe. But how does an AI actually think in a place like that? I mean, standard neural networks are built for flat spaces. The solution is this really elegant repeating cycle. You can think of it like a 3-step dance. The system fluidly moves from its natural, curved home to a temporary, flat workshop to do its calculations, and then gracefully returns. It gets all the efficiency of flat space computing without ever losing the deep structural integrity of its curved universe. So step 1 is the log map. The best way to think about it is like this. The Earth is obviously curved, right? But if you're just trying to navigate a single city, a flat map works just fine. The log map does the same thing for the AI. It takes a small, local patch of its curved universe and projects it onto a temporary flat surface, which we call a tangent space. Now, on this temporary flat map, we can use the tools we already have. A standard neural network, an MLP, can do its calculations simply and efficiently. The computation is familiar, but, and this is crucial, it's always kept local. It always respects the larger, curved universe that it came from. And finally, we have the exponential map. This is like the system's geometric autopilot. It takes the newly updated information and guides it back onto the curved surface along the most natural path possible. These are called geodesics. They're the straightest possible lines in a curved world. This step makes sure there are no shortcuts and no violations of the universe's physics. Okay, so the AI can compute locally. That's great. But in a universe that expands infinitely, we run into a brand new problem: loneliness. How do related ideas, which might be separated by vast distances, ever find each other to form a coherent thought? I mean, seriously, if the neuron that represents sky is way over here and the one for blue is all the way over there, how do they connect? You can't just build a physical wire between them, it's not feasible. The system needs a much more elegant solution. And the solution is beautiful. It's actually inspired by biology. It's not about physical connection, it's about temporal synchronization. So imagine a huge orchestra, but all the musicians are scattered throughout a giant winding canyon. They can't see each other. But a violinist in one part of the canyon can hear the cello in a connected cavern, and they can sync up their rhythms. The very geometry of the canyon decides who can play in time with whom. And that's the core principle here. In this kind of AI, every little neuron is like a tiny metronome. Concepts that are meant to be together, like sky and blue, they learn to oscillate in perfect time with each other. They form these islands of synchrony, creating coherent thoughts out of pure rhythm, not wires. All right, now let's zoom all the way out. We have a universe, we have a way for it to compute locally, and we have a way to bind thoughts together. So what does all this really create? Well, the theory proposes something radical, that intelligence, and maybe even consciousness, is an emergent geometric shape. This leads to what's called the Phenomenal Manifold Hypothesis. It suggests that for any stable, conscious-like structure to emerge, its underlying geometry needs three things. First, integration. The whole system has to be a single, unified whole. Second, coherence. All its different parts have to be able to synchronize and, well, dance together. And third, differentiation. It must have a vast, rich, and complex variety of possible states, or thoughts. What this all adds up to is a fundamental shift in how we even think about developing AI. It's like we've stumbled upon a new law of learning. Just look at the comparison. The old way was defined by flat space and global computation. We tried to make AI smarter by just scaling up parameters, making bigger and bigger models that memorized patterns. The new way is built on curved local space. Here, learning happens by structuring the geometry itself. The goal isn't just a bigger model, but a better shaped model, one where intelligence is truly structured, not just memorized. This single line just captures the entire shift perfectly. In these new systems, geometry isn't just some clever way to organize data. It is the fundamental, physical law that guides how the system learns, how it thinks, and how it organizes its entire world. So, this is the question we're left with. For years, the path to better AI seemed obvious. Just scale it up. More data, more computing power, more parameters. But this new paradigm suggests a completely different path, one that asks us to think about what happens when intelligence isn't just made bigger, but is given a better shape to begin with.